So as okay, yeah, good. So as I was saying earlier, my work is in realizing this intersection. So I'm gonna go ahead and base this talk in a very structured manner. I'll talk about sort of what is privacy preserving machine learning, the mechanisms, at least I use. There's many other mechanisms to enable it, but I'll show like multi-party computations, differential privacy. I'll show you the one that's really gained my interest, which is a form of public key encryption known as homomorphic encryption, and then how that relates to TDA, which is that computational topology-based machine learning techniques. And then I'll show you sort of some work I've done that realizes that intersection. Okay, so there's a lot, like I said, there's a lot of data in this world where you really want it to be analyzed and you'd love for things to be done to it. But unfortunately, it's really protected, right? You don't want to outsource it without the proper protections. You want to make sure it's, lock and key. You want to make sure that someone's working on it isn't looking at things they're not supposed to. You want to make sure that maybe what they download isn't against the law, right? I have a friend who got in a lot of trouble they had a data set and they got in a lot of trouble for downloading it locally to their computer. So there's a substantial amount of data is being analyzed, but it's really sensitive and we want to outsource it. So is there a way that allows people who are perhaps they have greater computational resources, maybe they have a really nice GPUs, or they have a nice computing cluster, or they have a supercomputer. Is there a way to give and offload the sensitive data to them in a way that allows them to handle it without breaking privacy, but still performing the desired computations, right? So the way I'm thinking of this, and I love this picture, I saw it once from a talk from Kristen Lauder, who's currently at Meta, that this is the idea that cryptographers have had since 1980, where we want a way to protect the person handling it because we think of this data as actually radioactive. It's really dangerous to expose to the world, and especially you, because you have no idea what type of effects it might cause. So what are these barriers that protect Homer Simpson here in this picture against the uranium? We are thinking of homomorphic encryption. So homomorphic encryption is, sorry. So this is the same, I'm gonna move this down here maybe. Okay, is there a way to like hide this? Hide panel.
Floating meeting controls.
Okay, great, thank you. Okay, so I'll go ahead and give us background on homomorphic encryption first. I'll show you how that relates to privacy preserving machine learning and data science. From data science, I'll introduce topological data analysis for the purposes of data science. And then finally, my research, which is on this intersection of HE and TDA to realize a dual benefit between the two. Okay, great. So first, let's talk very briefly about asymmetric public key cryptography, right? So in a symmetric key crypto system, we have a shared secret key that is exchanged between the two parties using some key sharing protocol, like Diffie-Hellman key exchange, for example, where both the encryption and decryption key rely on the same secret key. That's why it's symmetric. It's symmetric between the two parties. Asymmetric key encryption, on the other hand, has a public key, which is quite literally public, and then you have a secret key, which are two distinct keys where the public key is used for encryption, but then, in a sense, anyone can send you a message as long as they have the public key, which is, again, public, so it's pretty easy to send someone a message. But to decrypt it, you use the secret key, and only you own the secret key, right? So only you can decrypt. So homomorphic encryption key schemes look just like that, where we still have a public key, but we have a secret key as well. And then we have one more thing called an evaluation key. And I'll go ahead and discuss what that is in a bit, but I'll sort of run you through the very high level overview of what a homomorphic sort of crypto system looks like. So in general, at least in the most, like, if you really boil it down, we have two parties. We have a client who is the data provider and maybe even someone who wants a task performed on their data. And then we have a computationally superior, but semi-honest and somewhat curious server, right? So what we mean by that is we have a server who they will follow whatever you tell them to. They will do the thing, but someone could look in and try and gain some insight. And alternatively, you also can't unring any bells. They're not intentionally looking to gain any information from you, but they will learn it if you're not careful. So how does the sort of high-level pipeline go? You have some private data here, and then you encode it to the server's exact specifications. If the server says jump, you say how high, right? So you encode it and then encrypt it using the public key. Okay, we've already discussed public keys for to encrypt data. And then you send it past what we call the trust barrier, which is effectively it's out of your hands now. You've sent it, it's in the internet, or it's in an email, or it's in a file. You send it over to the server side. Now the server, because of the way homomorphic encryption works, is allowed to do very basic operations on your data. Now basic here means arithmetic in general, so you can do addition, multiplication, and then you can forget about the other three things. Let's just keep this very basic for now. You can add and multiply, and also index rotation as well of vectors. You can do that as well. But the server can perform those operations on the encrypted data. And then once it's done doing exactly what you told it to, it sends it back through the trust barrier. So again, as a zip file, as an email, as something, sends it back to the client. So the client owns it now, and they use their secret key to decrypt and then get the desired result. So that is the high-level overview of a homomorphic encryption key scheme. So to add some more details, we explicitly treat the encryption as a homomorphism, where the encryption of two the addition of two encrypted numbers is equal to the encryption of their plain text output. Similarly, we can do the same thing with multiplication. Encrypted A times encrypted B is equal to the encryption of A times B. You know, there's a little caveats here regarding with overwhelming probability. Really, this means it decrypts to the same answer with overwhelming probability, but let's keep it there for short. And the reality is that is actually that's very powerful. Because these two, if you think about it, this becomes effectively the XOR and the AND operation, or addition and multiplication bitwise. That is a Turing complete set. And so you can make any computable function through a finite number of combinations or combinations of these two operations. So it's very, very powerful. And through that, we have something called fully homomorphic encryption. Fully homomorphic encryption allows us to really compute any function we can think of, because it enables, we have a procedure called bootstrapping, which effectively resets error that accumulates whenever these operations take place. Okay. So there's a couple different schemes that are really popular in the literature right now. The first one that sort of came to prominence was BFV/BGB. The reason that there's a slash there is because they're actually really similar. They're very, very similar schemes. The main difference is where they store the information. One of them stores it in the most significant bits. One stores it in the least significant bits. But it's that one sort of first come to prominence, and that really works best over finite field or integer arithmetic. CKKS is the next major player, which was made by Seoul University, and right now they even have a company called Crypto Labs, and that is mostly used for floating point arithmetic. So if the things you're working with are floating points, you use that one. And then finally, TFHE was made by Zama. That is useful for bitwise or Boolean arithmetic, and effectively, you can use either of the three, but there's optimizations internally that make them best suited for one application over the others. And as you can imagine, between these three, for most machine learning applications, at least in the literature I've seen, most privacy-preserving machine learning literature uses the CKKS scheme because of its floating point approximation prowess. Right? There's a lot of floating point calculations. There's a lot of layers when you do like a neural network that have a lot of decimals. You want to preserve those. So I've mostly seen CKKS scheme, and that's the one I'm most familiar with as well. It's also called HEAN, by the way, because it was originally introduced as homomorphic encryption of approximate arithmetic numbers. So you'll see that in the literature as well. But I think most people call it CKKS now. Okay, so that's a brief background on just homomorphic encryption in a purely cryptographic setting. Allow me to now introduce homomorphic encryption and its relationship to data science. So using HE, the idea is that someone who owns really sensitive data can outsource the machine learning computations, including both model training, which is where the server creates an encrypted model based off the encrypted sensitive data, and also inference tasks where they use that model to predict or classify certain predict or classify basically. Right? And so the right now, like at least from what again from what I've read, there's a lot of things that are currently supported. Like for example, a nearest centroid classifier is simply Euclidean distance, so we could easily imagine that being homomorphic encryption compatible. But there's also decision trees and random forests, logistic regression, and there's work done by Microsoft as well as plenty of other people actually that realize neural networks as well, both in the inference portion and also even in the training portion. Now, as you could imagine, homomorphic encryption-based training is quite computationally intensive and is also generally iterative. So there's still a lot of work being done there, but I will say inference seems to be like very well established among researchers, and it's like, yep, looks good. It checks out. Okay, so I want to give a brief example of exactly how we can think of one of those algorithms in a HE compatible sense. So I have logistic regression, right? And let's make it really simple, logistic regression, and let's make it the inference task. Learning on logistic regression involves an iterative process that involves sigmoids and activator functions, and I don't really want to go through that. But inference makes a lot of sense. So let's imagine that you have a trained model already. So that means that the server has a model that is either learned in it's somehow learned in the past. And to learn a linear or logistic regression and any regression, that means effectively you know the weight coefficient, right? You know the weight vector. So those betas are our weights or our coefficients of the regression. And then an incoming observation is this vector x1 to xn, right? Well, then this is your box standard logistic regression, but that can be realized as basically the dot product between these two vectors and then the addition of the intercept. So that lends itself very nicely into an HE compatible circuit, which does exactly what we just said, right? We're going to multiply. So imagine that you have your input, you have your weight vector, and then you have an intercept vector. Then very straightforward, all you're going to do is multiply these two. Again, and the multiplication there that happens is component-wise multiplication. You multiply them, you do the correct number of rotations where you add those rotations together to get this sum, and then finally add the intercept, right? So that's exactly how this reads. And now this is a very naive way. Of course, there's a lot of ways to improve this. The main one, of course, being doing it as a binary tree makes it logarithmic instead of linear. But as written, this has a complexity of 1 multiplication, n additions, and n-1 rotations, and its depth is 1 multiplication. Now, these words, I'm sure that some people in the audience know what these words are. Especially, I imagine most people know what complexity is. That's like a very computer sciencey term. But depth is not one that I encountered before working in this field. So I'm going to briefly explain like how to think of those terms. Okay. So yeah, so exactly right here, right? So what are the limitations of HE? It actually depends. It's related to those terms there. It's that 1, all desired functions must be realizable and implemented as an arithmetic circuit, right? So that arithmetic circuit can only consist of additions, multiplications, index rotations, and then we also don't want any conditional statements that leak private information. So for example, if you're really naive and I say, like an if statement, if you were to evaluate an if statement, like on like very naively, you would have leaked if a certain thing was true, and you've now just given information about your data, right? Also, it has to be a finite arithmetic circuit. I don't think I wrote finite, but a finite arithmetic circuit. Also, and so the complexity, again, is a limitation because we don't want to make things too expensive. Depth is a concern because depth gives a measure of how much error accumulates throughout the procedure. And finally, there's inefficiencies in implementation. So I'm going to go ahead and go over. So I think this has made sense so far because I've shown you that you can add and multiply. But these three are not so clear. I'm going to go ahead and show you each of these and explain what they mean in order. So that's what the next slide is. So there's complexity. So to overcome complexity, or rather, let's define it first. Complexity of a homomorphic circuit is the total number of operations performed between ciphertext and plaintext. And usually what we do in the literature is we're very explicit. We say exactly how many operations are done. You can do a big O thing, but generally it's really nice to have a very like skeleton, this is how many operations are done based off of this circuit. And I'll give you an example of how we overcome this, and effectively it's skilled implementation, right? Like in a way, this is very computer science-y. So if I tell you, hey, here's a ciphertext, and now calculate c to the power of 2n, right? Naively, you can multiply c times itself 2n minus 1 many times to give you a complexity of 2n minus 1 many multiplications. Or if you're a little bit more savvy, you can treat it as a binary tree, or rather, not binary tree, as a successive squaring to get you log of n many multiplications, right? So both end up with the same answer, but one has way more operations than the other. So that's complexity. Depth is a little bit more tricky. Depth is specifically talking about the number of sequential multiplications. So the depth of a homomorphic circuit is the smallest number of successive multiplications a fresh ciphertext undergoes in the circuit. If you ask the question, why is there no depth equivalent to addition, right? Let's think back, let's think a little bit, maybe even before this. So a detail that I didn't really go over, but probably deserves some level of explanation, is that these elements, that homomorphic encryption is based off of the learning with errors problem, ring learning with errors problem, actually no, LWE, but then it translated to ring LWE. And the ring that we work in, right, is this ring, the cyclotomic polynomial ring, where this n is a power of 2. Okay, so effectively, let's just think about these as polynomials. That's the way I like to think about it. If you think about these as polynomials quotiented by that cyclotomic polynomial, if you add polynomials together, you're not changing the degree of the polynomial at all. You're just adding the coefficients. But if you multiply two polynomials together, then what must be done? Well, if you multiply two polynomials, you have to add the degrees, and then actually you're in a cyclotomic polynomial ring, so you have to quotient it by if you go over the degree, right? So multiplication is actually the most costly operation here. So we have a really vested interest in the number of successive multiplications. So let's look at this little tree here. Imagine we want to get the product C1, C2, C3, C4. If you did it sequentially, then you would have a total of 3 multiplications here, and you'd have a depth of 3. Yeah. Versus if you really thought of this as a binary tree, that is, if you utilize parallelization, you can perform C1 times C2 and get the product. You can do that's reversed, oops, C3 times C4 and get the product. And then finally multiply these two products together, and now you only have a depth of 2, right? Your tree is only of depth 2, not depth 3. So depth is another one, and again, the way we overcome that is through parallelization. And finally, we have the last one is inefficiencies within our own within our ciphertexts. So I'll give you an example that generally has been well received to explain this topic. If I'm loading my dishwasher and my dishwasher takes an hour to run, If I load it with only one dish, then I would be like, I have the worst dishwasher in the world. It takes an hour to wash one thing. But then someone could say, well, why don't you just add 60 things to it? Then you wash all 60 plates in an hour. Yes, it still takes this amount of time, but the amount per plate is now a minute per plate rather than 60 and rather than 1 hour per plate. That concept is called amortized time. You're amortizing how long the procedure takes by being efficient with the space you're allotted to run all of those things simultaneously. So let's say that a homomorphic circuit takes t seconds to finish running. If the operations can be performed in a single instruction multiple data manner, which really means that here's a set of instructions, but you can run them all theoretically in parallel with each other. So they are not interfering with each other at all. And such that the k plain text can be encoded and packed into a single ciphertext, then the amortized time is t over k. So I have that exact same multiplication circuit from the previous slide, but I'm thinking about it as, okay, there's actually ciphertext one, I want to get C1, C2, C3, C4, and also D1, D2, D3, D4. Well, if you just follow this circuit, I actually do get that no problem. And it takes the exact same amount of time to do it, but I have effectively cut the effective time to do this in two, because I've done two ciphertexts for the same amount of time. So that is the last major hurdle we face. So those limitations are exacerbated by really large dimension data, right? You could imagine that if a complexity has an n in it, where n represents the ciphertext size, then you're only going to make it worse by having really, really large dimension data. So my solution that I propose, or not I propose, but a solution that it has been proposed that I really like is something we do in the plain text space, dimensionality reduction, right? What does dimensionality reduction allow you to do? It allows you to take, let's say that, this is like a nice little visualization of it. If you have a model here and you have your observation here, what it allows you to do is you can get a faithful but smaller dimensional representation of this guy, let's say half of it, same thing here, then you can encode and pack those two observations into a single slot and still run the model once. So this allows you to, and I mean, I even did it, that's half, right? If you could get it even smaller and smaller and smaller, you can pack in more and more and more. So this is my solution to those limitations. Again, it's very obvious how this reflects to timings, but complexity, because if you have a thing that depends on the length, you're making the length literally smaller. In depth, there are some circuits where the depth depends on the length of the ciphertext, but that's not always true. So mostly, these two are really the main ones. So what is my proposed method? What am I doing that makes my dimensionality reduction distinct from other techniques that have been done in the past? There's stuff like PCA, there's stuff like eigenvector decomposition, there's stuff like if you have an image, you can downscale and resize that image. What am I doing? Well, what I'm doing is using latent topological feature extraction to algorithmically extract, not learn, but extract distinguishing shape characteristics that are present with underlying the data itself. So I have a little example here of sort of a little like amuse bouche of what I'm going to be talking about. But if you look at the number 8, the number 8's most distinguishing feature is the fact that compared to all the other single digit numbers, is that it has these two holes that no other shape shares, right? So if you can somehow extract these two holes, you'd know that the fact that they're even present shows you that this is the number 8. That effectively reduces this 28 by 28 pixel image, so 784, into 2 dots, which then we do have to, well, not have to, but something that's very common in the literature in this space, which I'll go over, is vectorize it into a real number vector, and then you feed it into any model you want to predict it. But the point is that, yeah, at a very high level, you reduce this really, really high dimension image into really, really compressed information that encodes its topological complexity. And that makes things really efficient, as I will show you. Okay, perfect. So I've gone over HE, I've gone over its applications to data science, and I've shown exactly what I propose to do to help solve those limitations, and I want to use TDA. So it would be really remiss of me to mention that and then not give you some background on this topic. So I'm going to go ahead and do that right now. So what's the main motivation for TDA? The main motivation is that actually shape is really important for a lot of things. And in particular, shape is really, really distinguishing, right? So here's a really great example that I like a lot. It's called the data source data set. And what this data set has is every single one of these images have the exact same mean in the y and the x direction, mean in the y direction or axis, mean in the y axis, standard deviation in the x axis, standard deviation in the y axis, and even the same correlation coefficient. All of them, they all have that. So from just pure statistics alone, if you were blind to this, you would say, yeah, these probably look like they possibly come from the same distribution. But then you look at them, right? I pull the curtain out. I say, oh, no, that looks like a circle. That looks like a torus. That looks like an X. That's a star. That's a dinosaur. I probably don't want to classify these things as coming from the same distribution because they look so different from each other, right? So if there was a way where we could realize this shape, not even machine learn, not even like learn this shape, but realize it and extract it algorithmically, then that would help solve a lot of these discriminating problems where, yeah, we would like to extract this shape information so we can say, oh no, these two are definitely different, even though they have similar statistics. So the way that we do that is, and I'm gonna keep a very basic level. We're gonna think about point clouds because point clouds have a really nice connection to geometry. You can think about connecting dots and everything. So what we do is that we use tools from computational topology that are grounded in algebraic topology, where we effectively really play connect the dots. We have our point cloud, so you have a point cloud in space, and then as you allow something called a growth parameter. You allow this growth parameter to make epsilon balls around each of those points, and then you connect them together based off of if those balls intersect. And there are certain rules for that. I'm not going to go over those rules very deeply, but just know that like the core fundamental concept of connect things that are close together over time is sort of ubiquitous in this technique. Right? And that connection causes shape to evolve, right? Look at this nested family. So we call each of these a simplicial complex, and then this is a nested family of simplicial complexes called a filtration. It's like you're getting finer and finer and finer. So first you have these balls, and nothing connects because they're far away, except for those that cluster up there. Then in the next stage of the growth parameter, more things connect. And in fact, you get a little shape here. You get a triangle because all three of those mutually intersect at one place. This is a Rips filtration. So we fill in shapes if all three have a mutual intersection. And then finally, at this very last stage, we can see the creation of more complex shapes. And we even have a really interesting shape here. We have a hole. So that hole is we call that the birth of a topological feature because that hole cannot be deformed, right? So imagine you have a disk and it's filled in, like totally filled in, like there's nothing in there. Or sorry, everything's in there. Then through a continuous deformation, you can slowly shrink that into just a point. It's not too hard to imagine that. But if you were to introduce a hole like that, like a donut, right? Then try as hard as you might, you're never, ever going to get rid of that hole you're not going to compress this shape without ever getting rid of that hole. That hole is always going to be present. So that adds some topological complexity, adds some flavor to the point cloud, right? And so what TDA does is its flagship method, persistent homology, describes the topological complexity of a point cloud and uses those to augment machine learning models, okay? In a sense, it's not a model really, but you use it. It's like a really, really nice feature extraction. Okay. And the main sort of trick or tool of the trade that encodes all this information is something known as a boundary matrix. So this boundary matrix is effectively an encoding of that evolution of topological features, but presented in a really, really compact matrix representation that has effectively recorded the entire evolution, right? So if you take a look at, for example, maybe this column, I know it's maybe a bit hard to see, but if you look at a column A, B here, there's a reason it's filled in with A and B there, because it's called the boundary matrix, because those are the boundaries of that edge. The boundaries of edge A, B are the points A and B. Similarly, if you look at the triangle, the first triangle is in K cloud, right? And that triangle is, let's see, B, C, D right here. Yes, right here. That triangle has three edges, BC, CD, and BD, which are these guys. Now, there's a certain algorithm that we run on this boundary matrix. It's called the reduce algorithm, and that's the work I presented at ACM CCS, which allows you to reduce this matrix in a way to get, we call the reduced matrix, but this reduced matrix actually tells you something called the persistence diagrams of your point cloud. This persistence diagrams is exactly the information that we were trying to extract out of here, that this encodes, oh, you have a hole that was born here and then it died later on, or you have points here that have persisted forever, right? So if you can do this, then you can get this. And that's really this is sort of the thing we're really trying to get at. I presented this work at ACM CCS and it was very well received there. And I will go over, I'll talk about that maybe if I have some time after. But yeah, this is sort of the main tool of the trade for that step. And here's a great example of exactly when this is used. So there was a recent paper on breast cancer chromosome expression, and here's so there's two versions of breast cancer here. You have one that's pretty normal, and then there is one that's really aggressive, HER2+. And so what they did was they did this entire shape extraction algorithm, and this is the resulting simplices that resulted out of that at different growth parameters. And as you can see, there's quite literally even more shape differences that are apparent when it's sort of visualized this way. And it makes sense if you look at this point cloud, this is really condensed around zero, very tight. So there's really these nice tight neighborhoods here for this as things grow along. But here it's more dispersed, and even there's a spike around at this area, and that is reflected in the chaotic nature of the filtration at this growth parameter. So this has been used in real world examples. So TDA has seen major success if used in the biomedical data sphere, and that data in general is often very, very, very sensitive. So it would make sense why I want to realize this intersection, right? So this entire work is called, so this procedure where you extract topological information from a point cloud, you use it, and then you turn it into a persistence diagram that has the topological complexity. You turn it into a vector and feed that vector for use in any model of your choice. That is known as the TDA ML pipeline. That has, again, seen very, very good use in sensitive data, including also, I'm saying biomedical, but also in financial data as well. It's seen use in financial data, like if you think about stock markets, moving up and down time series, you can think about the points themselves as peaks, and then you do sublevel set persistence. But the point is, yes, this is a very well established and well used pipeline. Perfect. So now I think I have the proper background to talk about my work, which is realizing this intersection between the two fields. Why do I want to do that? Because there's a nice dual benefit that in my belief, right? I'm very confident in this belief that both fields offer each other. HE gives TDA provable privacy protection and security in the fields in which TDA has found its major successes, right? If the successes has found in cancer, genomics, DNA, those are all, generally speaking, patient data. So it would be great to allow researchers to continue working on those and even people to outsource tasks in that field, but now have privacy protection so that they're not like divulging sensitive patient information, right? But then TDA provides HE, this is what I'll be focusing on for today. A powerful dimensionality reduction to ease the limitations on HE's finite arithmetic circuits. Right? This is a really, really powerful form of feature extraction that can reduce complex point clouds to effectively varying levels of compression. So that is why my work is focused on creating the secure TDA-ML pipeline. So that is where every step here is effectively secured in terms of through homomorphic encryption operations. So the entire scope of the work is this blue lock. This green one is the one I presented at ACM-CCS and is currently under review in IEEE TDSC. And this red one is what I submitted to at Usenix, and I plan to submit a full paper of that either back to Usenix or perhaps PopEds as well. And this will be the focus of my talk for the remainder of the time, which is how can we take a feature vector, a topological feature vector, and use it to train a model, and what boons does that realize in the privacy-preserving machine learning world? So that process that turns those persistence diagrams that encode the topological complexity of a point cloud and turns it into a real valued vector amenable for machine learning is called featureization. Okay, so it's called featureization. And my question that my main research question on this front was how quantifiable are the gains that TDA's feature extraction provides to privacy-preserving models? And is there anything in the literature that we can perhaps compare this to in the past to see if we have any improvements, or if we can improve past work, or maybe even avoid some of the problems that they've had in the past as well? So what we did was we did a small experiment. We compared different featureization techniques against their naive counterparts, which has actually been done on the, as you can imagine, the very well-studied MNIST data set, right? Everyone uses MNIST now for logistic regression classification. So why do we choose that? One, MNIST is very well studied, so it's not off the beaten path to also study that data set. Two, it's been studied to death in machine learning specifically, and also there's work been done on doing MNIST training and inference on encrypted logistic regression, and the way that they sort of realized that they're like, okay, this is way too big. So what they did to downscale it was actually quite literally downscaling. They did downscaling, right? So what we thought was, okay, what techniques can we do in our space to get comparable results in terms of dimension? And then does that provide any improvement in terms of maybe accuracy or time or memory or anything like that? So how do we do it? Well, using tenfold cross-validation, we fit a logistic regression. Okay. Using tenfold cross-validation, we fit a logistic regression model using each of the following pre-processing techniques and compute the accuracy per fold. So what are they? So the first two are the non-TDA methods. You have the do-nothing method, which is the original 28 times 28 MNIST image. That might be my email. Then you have the downscaled and resized. We went all the way from 14 by 14 down to 4 by 4 MNIST images. Then we did one featureization technique known as Adcock-Carlson coordinates, which effectively are a featureization technique that realize the persistence diagram space as being finitely generated by certain generators in a really complex algebraic structure. But the point is that, yeah, this is one featureization technique where you can control the size of the feature vector. And then finally, we did a Gaussian mixture model where we attempt to fit Gaussians over, we attempt to fit Gaussians over the points in the persistence diagram. And we chose 35 because that's what, so we did a study about, there was a study done of comparing featureization techniques on the MNIST data set. Well, MNIST was one such data set, and that was their default parameter. But there is one that we made here called the drop weight GMM, which will be the next slide. But the point, and that one is interesting because we realized that a lot of these features actually mean nothing. And so we dropped them because they were so low weight. So as a reminder, here's the logistic regression inference circuit, and we ran this circuit on each of these techniques after training the models. So yeah, let me give a little bit of insight to what we were thinking about for this guy. So if you think about the original MNIST data set, it's 28 by 28, so 784 dimension. Then what Barnes et al. Did in their TDA comparison paper was they did GMM, and so, okay, 35 Gaussians times 2 dimensions, H0 and H1, counting the number of connected components and holes respectively. And then they swept the image, so if you think about age, they swept it in 4 directions to get all possible features. And so they did, so that's why there's a times 4 factor, that's 280, right? So what I did was, okay, do we really need all 280? And the reality is no, right? If you go from 280 here, so what I did was I took each of those features and dropped them per weight and realized that no, you can get really high accuracy by dropping a lot of these really low weight features. So this is a little experiment. And yeah, in fact, there's almost no drop in stability nor accuracy until around this area, right? So I chose 130, and actually I chose 128, so I dropped 2 more because it got really close. And also 128 is a power of 2, which makes encoding much easier. Okay, so how do we verify our results? For each of the methods, 100 testing observations from the very last fold were extracted, encrypted, and fed into the LR inference function. And after decrypting those answers, the first major thing we found is that there's no errors in the encrypted prediction, right? So after decrypting the encrypted results and taking the argmax, we found that, yeah, everything predicted correctly. There was no discrepancies. If it was predicted as an 8 in the plain text, it was an 8 in the ciphertext. No errors at all. So that was our first major takeaway from this. Our next major takeaway is that the TDA-based methods outperform their naive counterparts. So what do I mean by this? So I have a little visualization here, this is for my poster. But effectively, we plotted the mean test accuracy as well as the log of the amortized runtime to get things more compressed. And effectively, each of the naive techniques of downscaling or resizing has, in a sense, a natural predator, where there is a technique that is both faster in time and also and at the exact same time also more accurate, right? And those are the TDA-based methods. So this red line is meant to indicate that to ease the analysis, I don't want to really consider you if you're below the accuracy of the original one. So we put that there just as sort of a visual break so that you can see everything above it. But yes, every single one of the non-TDA methods has a method in the TDA space that absolutely beats it in both terms of timing, but at the exact same moment more accurate as well. So that was one really nice take. And then so that's one really nice way to see it. Another nice way to see it is through a table, right? So this is a table that also gives very similar information, but it's a little bit more explicit, where we have each of these techniques shown. And what I did was, okay, I just sort of recorded it all and said we should make a metric that compares that tries to get the best one of all the methods, right? So what was the most obvious one was, let's make a metric that weighs accuracy versus runtime, right? So that's what this ratio is. And so this ratio effectively says, okay, if you're below the accuracy of the original, you're negative. If you're more accurate, then you're positive, right? And then this fraction right here scales it based off of how fast you are. So what we noticed was that from this metric, again, totally arbitrary, but the point was to sort of just get what's the best of each type analysis. We see that GMM drop was sort of the winner in the TDA space. And then downscaled 14 by 14 was the winner in the non-TDA methods. And so we compared them and realized, and so we have a little bottom row right here of how much is this an improvement over the original? And how much is this an improvement over the best non-TDA method? And we see that, yeah, we have an increase in accuracy by 1.39%. But we can get about 10, depending on how you look at it, about 10 to 25 times faster than the original, right? So we can get really, really fast and more accurate at the same time through extraction of these features. And now we have a really interesting observation that we plan to expand upon in the paper, but I'm sorry, this is really small, by the way. I'll summarize it for you. So on the left half is the non-TDA preprocessings, rescaling and downscaling respectively. And on the right side, where things are really high, is the TDA methods. And something that I did was, okay, I have an experiment. I wanted to run something and it seemed to have borne some fruit, which was, do we really, like, in a sense, logistic regression is great and all, but there's something annoying about logistic regression, which is that if you really want to implement it properly, at least out of the box, you're going to have to use those softmax activator functions, which, as you know, are non-polynomial, right? In the literature, you have to approximate it using Taylor series or Chebyshev polynomials. And so something that I thought of was, let's just do basic linear regression. That is, let's imagine that you're trying to classify, the classic example is 3 versus 8. Okay, now let's encode this to be -1 and +1. Well, I just trained a linear regression, not logistic, linear regression, and made 0 the cutoff point. And if my model predicted a number was negative, then that was a prediction as 3. And if it predicted my number was positive, then that had to be 8. So that is, I made a very arbitrary cutoff point and redid this using this new model, this new classifier. And through this really, really naive classification method, actually, it's not bad. It's not bad, right? So the linear regression is this orange one. And something really interesting to note is that all of these guys, doing linear regression without logistic regression, it beats all of these non-TDA methods using logistic regression, right? So even using a slightly more rudimentary approach, this really arbitrary cutoff point, it's still superior in terms of like classification accuracy and everything. But of course, per weight class, the logistic regression beats it each time. But yeah, that's a really interesting observation that, like, in a sense, I can still beat out an actual real logistic regression model by using a stronger pre-processing technique. So in a sense, there's some information extraction that's going on there that is really model agnostic in a way. Okay, so what's my future work planned in this space is that I sort of have this in the reverse order. I probably should fix this eventually. But the next major step is to perform training on these topological feature vectors. We plan to do training and then publish that somewhere, hopefully, again, at either Unix or Puppets. Improve the existing methods that we have to make it practical, and then securely vectorize. And then the last sort of major step is we want to think about securing the step which vectorizes a persistence diagram into such a real valued vector to use for downstream machine learning, because then that would feed in directly into the work we're doing right now. So that is turning secure vectorization is like project number 3, really. And yeah, that's my talk. Thank you. So you guys are my guinea pigs to see if this works. I tried making I made a QR codes on these locks to see if they would scan. And so you're now my hostages. So please see if this scans properly and if it works or not. If not, then it's fine. It's science. Oh, I see. I saw.
First one is you, right?
That's me. It's my Google Scholar. And then the second one is the archive paper for that, and then the third one is a PDF of my poster from Usenix. So if it doesn't work, that's fine. This is an experiment.
That's all works.
Ah, yes. Yes.
You pretty want to put a disclaimer saying that you are not charging people's money by.
Yeah.
You know, lots of money to come from security background.
Well, these were not like this. Okay.
It works for me.
Okay.
Oh,
Okay. So, but it works. Okay, great.
Okay.
Okay, so you know what? I'll take a 50-50 hit rate. But yeah, that's my work. Thank you guys so much.
There's, we have with our meeting too, so.
Okay.
Any question, a quick question, if there's, so we have time. Otherwise,
Maybe I just have one quick question. What is the typical dimension of the matrix that you're dealing with, like in this persistent?
Yeah, so it's totally filtration dependent, but if you want to get like it can range from n choose. So if let's say you have the number of points as n, it can range from n choose 2 or all the way to like 2 to the n to the power set. It's filtration dependent and also like how deep, how many like rather how deep in the homology do you want to go? Like that is like H0, H1 if you want to go off, want to go very deep.
So what is the typical size for n itself?
And itself, oh, I mean, depends on the, yeah, let's say, so it depends on the use case for what you want. So I'm just trying to think about like, right, so I'm trying to, right, even here, for example, I think n was quite large, n can be quite large, like there's probably like 1,000 or 1,000. Yeah, it's like literally the number of points.
So potentially there's no way you can fit it into a single ciphertext. So you have to.
Yeah, potentially not. Yeah, exactly. And that's one of the major limitations of this paper that we addressed in the work. And that's why one of the techniques we're really we're want to explore into and for this improvements is we want to look at computing persistent homology in a parallelized way by subsampling the points and then doing that in parallel.
That's a great idea.
Thank you.
Okay, I think.
okay, so thank you.
I know you have a department meeting.